A plus B. So here we have
is it 2mg k by 2mg?
2mg k by h bar square k square, which is the same as 2mg by h bar square k. Okay, so the thing is, you have C which is A plus B. A plus B minus A plus B is equal to gamma. I come. The sign is very important actually, so let's get the sign right. Is this okay? So this is the equation. I am throwing away this A, so I get that B times 2B 2 minus I gamma is equal to I gamma A. Let's not put the 2 here. Yeah, unnecessary. Let's not put the 2 there. I'm just redefining my gamma. I don't want unnecessary 2 factors there. So let me redefine my gamma without that 2 here. So if I do that, this half will remain, then 2b by b will just become b. We have a 1 and then very good. So we have discovered that b is equal to I gamma over 1 minus I gamma times a. Very nice. We have expressed the reflection amplitude in terms of the incident amplitude. Similarly, you are trying to find C. What is C? A plus B. So A plus B, what is going to be? 1 minus I gamma plus I gamma by 1 minus I gamma times A. So C is equal to 1 over 1 minus I gamma times A. C is A plus B. So this thing is 1 times A. So we have found C and B in terms of A. They're complex numbers, notice. These are amplitudes, probability amplitudes. Now we are ready to write the reflection coefficient. R is this ratio, JB upon JA. Remember the formula for JB and JA. H bar k by m times mod a square or minus h bar k by m mod b square. We take the ratio of all those h bar k and b cancels out. This is simply mod b square upon mod a square in this case. See, it's important to define the reflection and transmission amplitudes in this way, not simply as b squared by a square. Because if the asymptotic value of the potential is not 0, suppose at left it is 0, but at right the potential reaches 1 or something. Then how will you define the diffraction and transmission coefficients? It is not simply b squared by a square. It is that, and you have to work it out. So that's an interesting problem that sometimes in textbooks. That is, you consider scattering not in this kind of potential, but maybe a step potential. Then the formula for the reflection and transmission coefficient is slightly modified, but if you use this, it will always work. Because this has a physical meaning. Meaning is the reflected probability current divided by the incoming probability current, a very physical quantities. Good. What is this thing now? Mod b squared by mod a squared is equal to gamma squared over 1 plus gamma squared. By taking the absolute magnitude squared, so the absolute magnitude squared is simply gamma squared. Gamma is real. And 1 minus I gamma magnitude squared is sum of the squares of real and imaginary parts. E is equal to 1 by 1 plus gamma squared, which is mod c squared by mod a squared. Okay, so sorry. Yeah. Notice that R plus T is equal to 1. This is again a statement of conservation of property. Particles are either reflected or transmitted There's nowhere else to go. Good. Now, our job is not done. There are some more issues in this which will be discussed in the problem set. However, in the remaining time, how much time do we have? 15 minutes. Excellent. So I want to now introduce an important concept in scattering theory called the scattering matrix. So there's more to this problem which we will discuss later on. Now I want to introduce a new concept which is called the scattering matrix. It's a convenient way of packaging lot of the information in the solution to the scattering problem.
Before that, do we plan to calculate that one eigenstate here?
The bound state. Yes, we do plan to do that, but not in the conventional way. We will get it through scattering theory. The remarkable thing is that if you completely solve the scattering problem, you can also find the bound states. Okay? So that's one of the problems, and Vishnu will say how you can get the bound state energy using the S matrix.
And also, if gamma is 0 here, then completely will be transmitted, right?
Very good. In fact, okay, let us spend 5 minutes discussing the answer. I have not done that perhaps. Okay, poor scattering matrix will get postponed. So, let's look at this. See, gamma is the strength of the potential. So, if gamma goes to 0, how can gamma go to 0? No, what's the physical meaning? Either strength of the potential is very weak or energy is very high. Gamma is 0 if G goes to 0 or E goes to infinity. Right? High energy scattering or very weak scatterer. In both cases, gamma goes to 0. In that case, what would you expect? No reflection, full transmission. So we would expect T go to 1 and R go to 0 in that limit. Right? Weak potential or high energies. So let us look at a plot as a function of gamma. Let us plot T and R. See, because T plus R is 1. If you know one, you know the other. Let's look at the other limit. When gamma goes to infinity, that is very strong scattering. Then, yeah, you have a question. Yeah, energy is very low. E going to 0, very low energy. Then you might expect that the potential plays a big role. In fact, let us turn our head upside down. Notice that if I replace an attractive delta function potential with a repulsive delta function potential, G will go to minus G, gamma will go to minus gamma, but T and R will not change. Interesting observation. So, repulsive delta potential, that is G negative. So I make G negative, it will go from this to that. Very strongly repulsive point scattering. You can understand that problem. Because the barrier is very tall and very sharp, very strong, then if the energy is relatively low, it will not be able to climb over, it will not be able to tunnel. So in that case, for for low energies, there should be no transmission. So we will expect T to go to 0 and full reflection. So we notice that in this problem, whether it is an attractive or repulsive delta potential, the reflection and transmission coefficients are the same. I am now ready to plot them.
No, it's a general question. This sort of thing happens in classical waves, right? Now
waves like waves that are kind of a string hitting a wall.
Hmm.
So say